Hello, Internet. We are live.
Hey, everyone. Welcome to the Stanford MLSys seminar series. This is episode 14. I'm Kran. We have with us today Dan, Piero, Fyodor, and our guest today, Anna Goldie. I want to introduce Anna first. Anna is a staff research scientist at Google Brain, and she co-founded and is the tech lead for the machine learning for systems team there. She's also doing a PhD with Chris Manning at Stanford, and before this she was at MIT doing a bunch of cool stuff there as well. So today Anna is going to be telling us about chip design using RL. As always, the plan is going to be a 30-minute talk followed by a 30-minute podcast style discussion where you, the live audience, can ask questions. While Anna is talking, feel free to put questions in chat and we'll try to get those across to her after her talk is over. So today's topic is like chip floor planning with deep RL. So Anna, take it away.
All right, thank you so much for this introduction, and yeah, very excited to be here. Let me share my screen. All right, so you can all see my slides?
That's great.
Okay, so today I just want to start off with a little bit of motivation. I'm sure that, since you're all here in an MLSys seminar, you're probably already sold on this, but basically, in the past decade, systems and hardware have transformed machine learning. It's fueled massive progress in the effectiveness of machine learning. And I believe it's time for machine learning to return the favor and transform the way in which we design systems and hardware and just close this loop. And just furthermore, we need significantly better systems and hardware in order to keep up with the computational demands of AI. So here in this chart from OpenAI, you can see that between 1959 and 2012, compute usage has been doubling roughly every 2 years, and that was keeping somewhat pace with Moore's law. But since 2012 and the rise of deep learning, the amount of compute being used in the largest AI training runs has doubled every 3.4 months. And actually, Moore's law has ceased to hold, so we need to do something to close this exponentially growing gap between supply and demand and allow AI to continue to progress at its current pace. And so here I'm going to share some high-level takeaways from the talk I'm about to give. Basically, in this work, we developed a chip floor planning method, a deep reinforcement learning method that can outperform or match human expert performance in under 6 hours, whereas human expert baselines can take weeks or months at an extremely high opportunity cost. Superhuman chip floor plans generated by this method were used in Google's latest AI accelerator, TPU-v5. It's actually been taped out, and the work is currently under review by Nature. It's generated significant media attention, which is flattering, but now let's get down to, what is the actual problem that we targeted in this work. So basically, we developed a method for chip floor planning with this, which is the engineering task of generating the physical layout of a computer chip. But at a high level, this is just a form of graph resource optimization. So we take in a graph of chip components like macros, which are memory components, and standard cells, which are logic gates like NAND and NOR. And all of these components are connected by wires. And we want to place this graph onto a 2D canvas such that, it's not really 2D, but we can get into that later, such that we are minimizing various costs, like latency of computation, power consumption, area, while adhering to hard constraints like cell utilization or routing congestion. And this is a very complex problem. So previous towering challenges in AI, like Go, have only 10 to the 360 possible states, whereas a simplified version of the chip placement problem can have 10 to the 9,000. And there's been decades of prior work on this problem. Prior approaches fell into 3 broad categories: partitioning-based methods like min-cut, stochastic or hill climbing-based approaches like simulated annealing, and analytic solvers like the prior state-of-the-art replace. And in this work, we propose a 4th category of approach, learning-based methods. And more specifically, we pose the chip floor planning problem as a reinforcement learning problem. And we train an agent to place the nodes of this graph one at a time onto the chip canvas. And at the end, we get a reward signal that we can use to update the parameters of our RL policy to get better and better at this placement task over time. And just to ground us in the Markov decision process of this problem, the state at each time step is a representation of the graph that we're placing, a representation of the current node that we're placing next, and a representation of the canvas onto which we place this graph. So for example, certain regions may already be occupied by previously placed nodes or other blockages. And the action at each time step is where to place the current node next onto this canvas. And then the reward is, after placing every node, we can take the negative weighted sum of approximate wire length, congestion, and density, which are key metrics in measuring the quality of a chip layout. And just to be even more concrete, our objective function here is, given a set of training graphs G, we want to maximize the expected reward, where the expected reward is just this negative weighted sum of wire lengths, like the total sum of the lengths of all the wires connecting these components given this placement, congestion, routing congestion, and cell density. And so here I want to share some early results that we got on a TPU v4 block. Unfortunately, I have to blur these placements because TPU designs are highly confidential and in fact subject to export control. But here I want to just give a qualitative picture of the differences between the types of placements that human experts generate and those that our deep RL agent generate. So you can kind of see that the RL agent generates these like rounded, smoother kind of placements. And actually this results in lower wire lengths, higher quality placements. And it can do so far faster. So the human placement on the left took 6 to 8 weeks, and the placement on the right took 24 hours. And since then, we've actually significantly reduced the runtime of our methods, and we can get higher quality placements in under 6 hours. And I'll show more results later in this talk. So basically, at that moment in time where I showed you that placement, we were in this previous regime where we would train the agent just on the task of learning how to place one particular chip netlist onto one particular canvas. And it would still need tens of thousands of examples or iterations, episodes, in order to be able to learn how to do this task. And in the end, it was superhuman, and maybe that's still useful. Like you could still maybe use those placements in an offline, it's an offline task. But in some sense, it's not as interesting. It's not satisfying from a research perspective. And also, like, just in terms of actual impact, it would be nice if you didn't need tens of thousands of samples in order to place each new netlist. So we wanted to move towards this kind of new regime on the right, where we pre-train this policy on the general problem of being able to place any chip netlist onto any given chip canvas. And then maybe when we see a new previously unseen chip, we would need fewer samples, maybe only hundreds of iterations, or even 0 iterations, and maybe at 0 shot we could generate a decent quality placement. And so that's what we were working towards next. And the first things we tried were kind of the obvious things. Like we took this architecture that we had been successful at maybe not generalizing, but just being good at the placement task of doing one particular placement at a time. And we tried just pre-training in a number of blocks and applying it to a new previously unseen block. And the results were very poor. We tried various different schemes, like we froze different layers of this policy and pre-trained it and then applied it to a new one. And that also didn't work well. So the question is, like, in the end, like, what did work well for us? And actually, it was leveraging supervised learning to discover an architecture that would be able to produce generalizable representations of this input problem. And so the insight here was that when we examined the performance of this previous architecture on this generalization task, we found that the reason that it did poorly was because its value net was very inaccurate at the prediction task. It didn't have a good idea of like the quality of placements of netlists that it hadn't placed itself. And so the insight here was that we could decompose the problem and kind of this, if you cannot accurately predict the quality of placements, then probably it's unrealistic to think that you would be able to actually generate high quality placements. That seems like a strictly more challenging task. So we're like, let's just break it down. We'll train models that are able to perform the general task of predicting the quality of placements of any given netlist. And we can use that as like an encoder in our RL agent. And so in order to train this supervised model, we needed a labeled training data set. But the good thing is that we actually have an agent. We have this RL agent that can generate any number of placements we want for the net list that we have available to us. And we can, generate a range of qualities because we can capture placements at different stages of training of this agent. So at the very beginning, when these placements are almost random, very low quality. And at the very end, we have placements that are actually superhuman. So, we have a broad range of qualities. We have a number of different chips that we can place. And so we generated a labeled data set of 10,000 examples of placements and their proxy costs, the approximate wire length and congestion costs associated, basically our reward function. And then we tried, so we basically now we have this playground where we can easily test different architectures and measure, the effectiveness of these architectures at generating high quality representations that can be used to perform predictions of these reward function costs. So basically what we're varying here is this graph convolutional neural network here. And what we pass to that network is features of the nodes and of the placements of this graph, like the x, y coordinates, the width and heights, the types of the macros, and other properties of the graph. And then we feed this information into a graph convolutional neural network, which we pass to two different fully connected networks, one that predicts wire length and one congestion. And we tried various different architectures here, but it was far easier to test because we had this sort of supervised learning setting. To do so in an RL setting is far noisier and more challenging. And what we landed on, and I'm going to explain more how this algorithm works in a minute, but just wanted to give some high-level intuitions first. Basically, what we landed on was this novel edge-based graph convolutional neural network. So basically, prior graph neural networks tend to be much more focused on properties of nodes in the graph rather than of the edges in the graph, which makes sense in a lot of settings, like, say, social networks. But here, if you think about it, the key metrics that we care about, like, say, wire length, are very much related to properties of the edges, and other metrics that chip designers care about, which I haven't talked about yet, say timing violations, are related to things like the longest path within this placement of the graph. So that's also very much related to edges. So it kind of makes sense that treating edges as first-class citizens would help us build more meaningful representations of this chip netlist graph. Okay, so the way that this graph embedding works is that we pass properties of each of the edges in this node into a fully connected model. So we initialize a representation of each node. To get the initial representation for each edge, we just concatenate those representations. So basically, we concatenate the representations of each of the nodes that edge connects. We pass that into a fully connected network to get a representation of these edges. To get a new representation of the nodes, we just take the mean of each of the edges that it participates in, and we just rinse and repeat. In practice, we found that performing these 7 iterations of this algorithm gave us good results. So in practice, that means that the representation for each node is influenced by the nodes within its 7-hop neighborhood. And at the very end, if you want a representation for this entire chip netlist graph, we can just take the mean of all of the edges in that graph. Okay, so that's what's going on here with this graph convolutional neural network. And we're just feeding this into a very lightweight, fully connected model at the end to predict wire length and congestion. So let's see how did we do with this architecture. So here, I'm showing the correlation between the predicted wire length from this network and the actual reward function, wire length reward function, and the congestion congestion reward function. And as you can see, the correlation for wire length was very strong. For congestion, it's a bit noisier, but that cost function is itself quite noisy. And I'm going to show you how this sort of plays out in terms of the end performance. And just to explain sort of how this fits into this larger policy value architecture, or how did this, we use this in our RL agent. It's effectively the encoder for this policy and value network. So we use this graph convolutional neural network to generate embeddings of the edges and of the nodes, the macros, and we pass that into the policy network, which makes actual predictions for the probability distribution over locations in this canvas for where to place this node next, and the value network, which predicts the quality of this placement so far. And it kind of makes sense intuitively that these representations would be helpful certainly for the value network. And we also make use of a mask function. So if certain placements would be invalid, say like you're not allowed to have macros overlap with each other, we can actually just forbid that. So not only does that prevent some possible invalid placements, but it also prunes our search space and makes our method more computationally efficient. So here, I'm showing you some results on an Ariane RISC-V CPU. So this is an open source chip I can actually show you. So on the left is a policy that's trained from scratch. Each of these squares is a macro. And on the right is a policy that was pre-trained on a number of chips, and it's being fine-tuned on a new chip it's never seen before. And as you can see, at 0 shot, after less than 1 second, it already kind of has this shape, this rounded, this region in the center where it leaves clear to place standard cells. And this results in a higher quality placement. On the left, the policy that's trained from scratch eventually converges to something pretty similar, though slightly lower quality, but it takes far longer. And so here I'm showing you the convergence curves for these two policies. So the blue line is the policy trained from scratch. The green line is the policy that's pre-trained on a number of chips, and now it's being fine-tuned on this new chip netlist. And as you can see, it takes over 40 hours for the policy that's trained from scratch.
Hey, Anna, I think, oh, never mind. The slide just updated. We were still on the animation for a bit, but all good now. Now we see the blue and green curves.
Okay. Yeah, so I can start again and give you guys a chance to actually be able to see this slide. So here, the blue line is the policy that's trained from scratch, and the green line is a policy that was pre-trained on a number of chip netlists and is now seeing a new netlist for the first time. And as you can see, it takes like over 40 hours for this policy trained from scratch to converge to something similar to what the pre-trained policy can achieve. Okay, so finally, I just want to show you the effect of the size of the pre-training data set on the convergence of the model. So here, the x-axis is different amounts of fine-tuning, and these green bars represent different sizes of pre-training data set size. So the green line is a small data set with 2 blocks, blue is 5 blocks, and yellow is 20 blocks. And what's kind of exciting here is that even going from 2 to 20 blocks, we already see dramatic improvements in the quality of the 0-shot placement. And that gives me hope that if we could get access to more designs, either through augmentation, or maybe if people open sourced more of their designs, we could have 0-shot placements, like meaning placements in less than 1 second, that rival placements that took tens of hours to generate. And this would have implications for like the overall or end-to-end chip design process. Like if you could get a clear signal of, given a netlist, how high quality of a placement or what performance qualities a placement of that netlist could have, you could do all sorts of design space explorations, at the architectural level. So I'm optimistic about those sorts of progress. So finally, I want to show some, raw metrics here. So here we're looking at 5 different blocks of TPU v4 and comparing replace, which is its prior state-of-the-art automated method, an analytic solver, manual, which is in some sense the real prior state-of-the-art, human expert placements spending human experts, like actual physical designers whose job it is to generate manufacturable layouts for TPU blocks, and these were the actual layouts used. And it took several weeks. And then our method, which is this deep reinforcement learning method that I just described. And so the metrics here that we're comparing on are the timing, area, power, wire length, and congestion. These were measured with a commercial EDA tool, electronic design automation tool. And these measurements take up to 72 hours to generate, but they're highly accurate, and they're kind of the gold standard. These are the numbers that humans use to decide like which layouts to actually manufacture, and these are the metrics that they care about in making those decisions. So as you can see, we compare quite favorably to these prior approaches. And with that, I just want to thank all of my collaborators. So this was a collaboration between Google Brain and the TPU team who built these accelerators. And here is a link to the Google AI blog post, as well as our archive preprint. And here is some other work by the Machine Learning for Systems team. And so if you're interested in other machine learning for placement or combinatorial optimization problems by our group, feel free to check out these papers. And thank you so much for having me on this seminar, and happy to answer questions.
Awesome, thanks so much. Yeah, let me just I guess take a quick look at chat. Yeah, just a reminder to folks in chat that they can start asking questions and post them, and we will get them across to Anna. Yeah, I guess to just start us off, one of the things I was curious about was a lot of reinforcement learning starts off with having access to the simulator, right? And to build that, you first need a reward function, which you talked about maybe briefly. I think you alluded to the fact that some of those rewards are actually fairly noisy. So I'm curious about the work that went into building that simulator and kind of that pre-work before you were able to do this. And then how you kind of thought about designing this reward function. I think one of the things you mentioned was some of these are actually there's other constraints like timing and stuff, which didn't show up here. So I'm just wondering if how that works and how these are correlated to each other and so on.
Sorry, I couldn't hear the second thing you said.
Oh, sorry. I was just saying how you decided to arrive at this particular reward function, because in the table, for example, you were showing timing and other concerns as well. So I'm just curious how that process was like.
Yeah, that's a really good question. So I think, yeah, in RL, really at some level, it's all about the reward function. In this talk, I've been focusing on the architecture, how to build representations, and obviously that's important for generalization. But I think you really can't get anywhere without reward functions that are fast and which are, actually measuring something at least strongly correlated with what you actually care about. So here, how we arrived at these reward functions, in some sense, there's, how much they relate to what we care about, and then how expensive they are to measure. So as I said, this was a collaboration with the TPU team. So we actually had chip design experts working with us, which is really, really helpful. So the TPU team developed this proxy wire length cost that could be measured in, I think milliseconds, very, very fast, as well as this congestion reward function. So you can approximate the total length of all the wires in the design very fast. And that correlates with other metrics that you might care about. So say in this table, and I'm happy to explain more about what each of these metrics mean. I wasn't sure how interesting it would be to people, but for example, timing, where it's negative slack, total negative slack, these are measures of sort of timing violations, which have, which do relate to kind of the longest path in this, given this layout, this placement of this graph. So those are kind of related to wire lengths in some extent. And power is actually also related to wire lengths, and that's obviously something that matters, and it affects how much it costs to say deploy a chip in a data center and use it over many years. So wire length is something classically in sort of chip design literature. Wire length, if they were going to pick one metric, is kind of the metric that they would use, even though in and of itself maybe it doesn't matter, but it tends to correlate with the things that do matter. Does that make sense? And then, yeah, and then in terms of congestion, so congestion is related. So I sort of alluded to that, we're treating this as if it's we're placing a graph onto a 2D canvas, but in reality, the canvas is of course three-dimensional, and there's some number of layers or some wafers, and it's actually a grid, so it's not actually continuous. There are certain places in which the wire can pass either vertically or horizontally. And if there are, say, 12 layers, you cannot have a wire pass along the same, on the same layer, in the same coordinate, in the same direction. So you can actually exhaust your routing resources. And so congestion is a measure of whether you're consuming too much of your routing resources, and it's actually going to become impossible to route this design. And so there's actually kind of a trade-off between wire length and congestion in some sense. If, let's say you wanted to make wire length 0, you could just place all of the components in one one spot on the canvas, and then wire lengths would be very low, but say congestion would be extremely high, like impossibly high. So in some sense, by having the RL agent simultaneously optimize both wire length and congestion, maybe you can create this sort of, you can trade off effectively between these two metrics and kind of land on a design that will actually, you know, be high performance, but in fact fulfill, like, adheres to the constraints of the problem. And, you know, also things like wire lengths do correlate with the other metrics that matter. And these wire length and congestion are also metrics that we can approximate very quickly. So those were all the considerations that we had in mind when we were designing it this way. And in fact, we're also working on incorporating, say, timing cost functions more directly. So timing is a lot more expensive to model, but if you could do so quickly, in some sense, you're representing what chip designers care about in a more direct sense.
That was a great answer. Yeah, that was basically what I was trying to understand.
Okay, I'm glad that I answered your question.
And you spoke a bit about generalization a couple of times throughout the talk. I was kind of wondering, what does like distribution shift look like in this problem space? I think, you know, in, you know, I don't know, image classification, things like that, people have like a good idea, you know, a bird looks like one thing and another bird looks like something else. But what is kind of the equivalent here for what your agent kind of has to learn?
Okay, yeah, maybe I think it's good to give a picture of this, right? Because I think in some sense, like, people are surprised sometimes when, let's say, I talk about, oh, like, initially our policies didn't generalize and then we trained them to do so. It kind of, like, at first glance, you would expect, of course, you would train from the beginning a policy that generalizes. But in fact, these chip netlists can be quite different from each other. So, like, you know, a given chip can have, you know, it could have like 6 macros, or it could have thousands of macros, and it can be connected in very different ways, and the canvas can look very different. So, like, it's almost like you're playing, like, instead of playing multiple different games of chess, you're playing multiple different variants of the game of chess, where instead of, you have, you know, instead now you have 1,000 rooks and you have 100 pawns and you have, you know what I mean, and they move in different ways, and actually the win condition now has changed, and certain regions of the board you cannot, you know, place pieces on anymore, you know, right? So, like, very different chips have different graphs, different sizes of graph, different topologies of graph, different properties of the nodes in the graph, different, like, regions of the canvas may be blocked. There can be blockages or clock straps that you can't place onto, and, you know, maybe different considerations for a given chip. Maybe you care more about power consumption for a particular chip, or you care more about area, which relates to the cost of manufacturing. So I think in some sense they are quite different, the problem of placing different chip net lists onto different canvases. Does that give a clear picture?
Yeah, I think that was really helpful. The analogy of playing a chess game with 1,000 rooks is, I think, you know, useful.
Hey, Hannah, I actually have a couple of questions that are pretty correlated with this. I would say the first one is, I'm actually curious of the, you know, failed attempts. What were they, and what are actually, what have you learned? What do you think, like, was the reason why those attempts didn't actually work? And the second one, which is really correlated, I'm aware of, like, one work actually I worked on in the past, but there's a new set of works that are trying to do meta learning with graph neural networks, and I'm curious if you think that could be also a viable solution in the future for you to explore.
Yeah, definitely. Yeah, in terms of, I mean, I admit these. I think this happened almost like 2 years ago at this point. But yeah, I think our prior architecture, at some level, it just wasn't generating meaningful representations of these input graphs, right? And so, like, basically the model would learn to overfit to the particular whatever variant of chess that it was playing in this case, but it wasn't really learning, like, core properties of the placement task itself. So, like, I think it just was a property of that particular architecture, not really the things that we were trying to do to, like, leverage that architecture. And I agree that I think it's maybe very promising to try some of this recent work on meta learning for graph representation in this problem space. And I think it would be really exciting to see that happen.
Hey, Anna, I have a question. It might be a bit naive, but suppose I wanted to design a new chip using an algorithm. What's in the way of me designing a chip that's just as good as the latest TPU?
I mean, I guess like the problem is to some extent that like, this chip floor planning is very important, but it's not like the only stage in the chip design process. So in a very oversimplified way of putting it, you could say that first you need to determine what's in the graph, and then you would need to place that graph. So, first you have to, automate that first step, the architectural design, logic design. You have to be able to decide what's in the graph and then synthesize that into RTL and then place that netlist now. So, and now you also need to perform design verification. So you need to verify the correctness of the chip as well. So those are kind of the important components or stages in the process. But yeah, why not do better than the TPU? So like basically that's what we're showing here in this table, is that if our method had been used in the previous TPU, it would have given better results. And actually we are used in the next TPU, and now we have even better results than the layouts that were taped out. And in some sense, we almost wish that we could tape those ones out instead. So yeah, there's no reason that you can't do better and better at these placement tasks.
And I'm also curious why the sort of emphasis on speeding up the RL algorithm, because as you pointed out, like it took them 6 to 8 weeks to do it. And you're already at 24 hours, which feels like a big win. So I'm curious what the motivation is for going from 24 to 6 hours. Because like, it seems like why not just spin up a job, do it 24 hours, and you have a new chip, right? Like, is this process going to happen more frequently? Is that the idea, or?
I think it's a very good question. Like, actually, like one of the Nature reviewers was pointing out, like, why are you so obsessed with going from 24 to 6 hours? Like, who cares if you're going from months to hours? And yeah, I think that's right. I think the biggest breakthrough is just being able to do it on the order of hours instead of weeks. But at the same time, like, I think as I was alluding to at the end of the talk, like if you can really quickly get a signal on, okay, so given what's in this graph, how good would it be if we were to place it? If instead of taking weeks, that takes, seconds, or like, very low number of hours or minutes, then you can do certain like co-optimizations. You can treat it as the inner loop for other optimizations at, say, the architectural level. So I think that's exciting. And then also whatever, I'm a machine learning nerd. So, to me, it seems a lot more meaningful if you can train an agent to solve this general task. And also just like, this work was confidential for a while, so we couldn't publish on it. And so in the meantime, we were, improving our methods. And that was, something we could make progress on. So there's that too.
And while we're kind of staring at this slide, we just had a question from a viewer that they pointed out that in a few of these blocks, I think in the TNS column, the one in worse is the one in hours is sometimes worse than the one in manual.
Yeah.
I imagine what this question is kind of getting at is that you're optimizing kind of like a few like very specific things in your reward function. But that doesn't necessarily always correlate to like an actual like better chip at the end of the day. So how do you think about, I remember you talked a little about this earlier about how they're kind of like useful proxies, but how do you kind of work through that, tension between something that you can easily measure and simulate and, the actual piece of hardware at the end of the day?
Yeah, it's a very good question and good catch on these numbers. Yeah, certainly, like wireless maybe correlates with timing, but it doesn't guarantee better timing. And as I mentioned, we're actually trying to develop very fast proxies for timing in a more direct sense. And that would sort of address the issue. At the same time, these timing numbers are all usable. So basically, if you notice, there's a subtle graying. So a number of the replaced placements are grayed out. And the reason is because they would be considered unusable by the physical design team because, for example, the WNS, TNS, or congestion are prohibitively high. Like you could never take this placement and close it or like modify it such that it was something manufacturable. So anything like under like 150, like say picoseconds for WNS, you can probably figure out some way to close that out. So in some cases we're worse than manual, but it's pretty comparable, and sometimes we're better. So that's I guess what I mean by comparable or superhuman.
Yeah, that's some really interesting context, I think, for our viewers. We also had a couple questions in the audience about kind of the search algorithm that wraps the reinforcement learning process. So I think Tinchel Jiang asked, at every state in time, are you only looking at the partially placed things or also the unplaced things? And Pat Langley was wondering, like, kind of do you start with an empty design, then add elements, or do you start with a random design and repair it? Kind of classic like depth first or breadth first search questions. So wondering if you have any insight there.
Oh, they're both good questions. So the first one is about, do we look at partial rewards? And then the second one was, do we start from a blank canvas or do we mutate placements as our action? And actually, those are both things that we've explored. So actually, the original algorithm, the one that generated this placement, actually did make use of partial rewards. So we would look at the impact after we placed a node. How did that improve the quality of the placement? And we would assume that all unplaced nodes were basically in the worst possible position that they could be in terms of how they influenced the wire length and congestion costs. That was useful for that first architecture. It didn't seem to provide as much value for this architecture that was capable of generalization. Maybe we can revisit that again in the future. We did invest the effort to make this sort of incremental cost function. But here, the results that I share at the end of this talk, they were generated using an RL policy that treated every time step as having 0 reward until the final step after we placed everything, and then we measured 1 reward. So the current point in time, we don't consider incremental cost, but I think it's very interesting. And then the second question, do we start from a blank canvas and place things, or do we mutate? So we've actually explored both. So at this moment, what we found is, right for now at least, we were getting better results for RL at least by using just by starting with a blank canvas and just placing everything. But we did in fact explore, we called it placer and replacer modes. So for other baselines, like we also have compared, say, against simulated annealing. So for simulated annealing, the action space would be just doing shift swaps and rotations of the macros. And it's not capable of placing from scratch, so we have to in order to be able to perform a comparison. We also outperform simulated annealing, but it doesn't do as well as art replace, so it's not included in the table. But yeah, I think that's also interesting to explore.
Well, I'm actually curious about what could be, the next steps for a project like this. I can imagine that, for instance, in order to bridge the gap with the lack of 100% correlation between the metrics that you're actually using and the actual timing, maybe you could learn a model that, given a placement and a graph, can actually predict its timing, and so use that as a proxy function, for instance. Or maybe there could be ways to coming up with the graph also, not only placing it, but also the design part of it. I'm really curious about what's next for this.
Okay, yeah, in terms of learning simulators, I definitely agree that that's promising. In some sense, the true cost is after you build the chip, you measure say its power consumption. That would obviously be too expensive. It costs millions of dollars to tape out a chip. Even those the EDA design, the electronic design automation tools, if it takes 72 hours to generate a sample, and the licenses cost millions of dollars per year, so you can't just run a million in parallel either. So even those are sort of prohibitively, it's hard to gather enough samples from that to, especially if you're on a research team and it's hard to justify using these production resources for your research project. I can't necessarily get enough samples to say learn the simulator effectively. But yeah, those are the kind of things that it would be very valuable if you could say train a model that was well correlated, and that's what we're working on. And then the other thing we're working on is, yeah, kind of what you alluded to. Can we do end-to-end chip design? Can we, say, leverage this fast placement algorithm to be able to explore, what would be effective components in this net list? Yeah.
The book is already super fascinating, but going in that direction makes it even more fascinating. That's amazing.
And I kind of had a sort of a higher level question about reinforcement learning in general. So I think, one of the things that you said that you learned from this project was putting kind of supervised learning in the middle of the loop was an important part of making things work, which is a pattern I think that we've seen elsewhere in reinforcement learning. Like I think AlphaZero use supervised learning to kind of learn what makes like a good chess position. Do you have any thoughts on kind of how necessary this relationship is between supervised learning and reinforcement learning? Is it something that's always going to be there in a successful system, or do you think like it will eventually reinforcement learning will kind of learn how to eat up the supervised portions?
Just to make sure it's clear, like it's not in the loop, if that makes sense. Like we used supervised learning to like kind of make this little playground where we could try out different like graph neural network algorithms that would generate like meaningful representations, and then we kind of just grab this component, this graph neural network here, and we just use it as the encoder in this policy model architecture. But in some sense, like we didn't even use the pre-trained weights that were learned with supervised learning. We probably should have done, but we actually got good results without even doing that. So in some sense, it really was just about trying out different architectures in a playground that was kind of easier and faster to test out ideas. And I think that's kind of where like things like meta learning in the context of graph neural networks would be like good to explore, right? But in some sense, like supervised learning is not actually in the loop here, or not in the same sense as with AlphaZero.
Gotcha. So you already have an example of a successful RL algorithm that doesn't do the same thing.
Yeah. And in some sense, like people often ask, like, oh, well, what would naturally make sense would be something like the progression of like AlphaGo to AlphaZero, where it's like they used expert humans demonstrations of Go games to like first to learn how to be good at Go. In this case, it's so expensive to design a chip. There are so few examples of expert demonstrations of this task that like we really couldn't rely on those. Like we had to have the agent learn it on its own in the environment, and in fact it can outperform humans. So like in this case we had to like move past that. Anyway, go ahead. Sorry, I didn't mean to cut off. Someone was asking a question.
No, my question was, I guess, are there other problems now that you're looking at that have a similar kind of placement flavor? I imagine things in networking and so on, and you talked about co-design as well. I know I've talked to you about that before offline, but I'm curious if you can talk a little bit about where this general direction is headed. And what parts of what you learned on this particular project do you think will translate well to other problems in system design?
Yeah, that's a good question too. And yeah, I can, as I alluded to these other papers that we worked on, in some sense, like we were inspired by some of our past work in other systems optimization problems. Like for example, device placement. We trained a reinforcement learning agent to take in a TensorFlow graph and place the nodes of that TensorFlow graph onto different GPUs and CPUs in order to, reduce the training time for like training the given input model. So like basically it matters a lot how you partition that graph. And so in some sense that was the inspiration for this work. And we of course we tried our hierarchical device placement method on this new target problem, and it could not scale to such a large problem, but it was in some sense inspiration for us. And then we've worked on a number of other things like graph clustering, and Yenqi's done a bunch of follow-up work on device placement that generalizes and also does other like tasks in this basically, so like, I think that there's so many different systems problems that we can treat as placement problems, and actually even outside of sort of the domains that we would think of as traditionally systems problems. Like, I've even been approached by, like, say, city planners, like Sidewalk Labs, was saying, well, what if we wanted to place buildings, and like, depending on how we place the buildings, and we treated them even as three-dimensional, it would affect the light that would come into the windows of these offices. Like, could we treat that as a placement problem with these types of metrics that we're trying to optimize? Or what if, like, I had a discussion with this faculty of MIT about, like, what if we could place dams, and like, depending where you place the dams, it affects like the flow of water, and it impacts like erosion and other properties of the environment. So I just think it's very placement is a very like fundamental problem.
Just as a follow-up, just curious, like, do you have stuff that you're putting out in the open source as well to, like, for example, simulators for particular problems, as well as just this general class of methods that you've been building?
I think that would be really exciting to open source more of this work, and actually that's something I'm working on or interested in doing. I think at the same time we have to balance, like, obviously I can't share anything that would give insights into the TPU designs if they're subject to export control. But I agree that certain things, like maybe even just releasing these cost functions, could be useful, because I think there's like more work we can do. We can do even better at this placement task, and it would be great just to have more people like working on this problem, and we can just all help make chips that perform better and use less power and such, right? So yeah, I think that would be great.
Yeah, I'm also curious about one other thing, which is how some of these chip designers actually responded to this kind of to the solutions that you do build out. You showed those like blobs which were blurred out, but I'm just curious, like, when they looked at that, they were like, well, we could never have done that because this is kind of crazy. Everything's like placed in this weird fashion. Or was it more like surprised that it's even possible to do things like this?
Yeah, I mean, yeah, you kind of nailed it. Like, they were kind of like, what the hell is this placement? Like, this just doesn't look right. And so, like, really, I think that the only way that we were able to get traction was just showing these metrics, because at the end of the day, really, this is what they should care about. And so if the numbers are good, then it should be good. But I think there is still this, like, it's so expensive to tape out chips, like, that these chip designers, they have to be somewhat conservative, right? They have to be careful about like what they proceed with. And so, like, I think to some extent it made them nervous to see these weird shapes, and it just seemed hard to believe that really that would be a better solution. But the numbers don't lie, and in fact these were actually taped out, and it didn't cause any problems, and these performance improvements persisted. But yeah, I mean, there's definitely also a lot of pushback, and that's part of why I'm like so happy that it actually landed in production. Like, it almost felt impossible at first. Like, people, they didn't even want to test the layouts. Like, they see a layout and say, well, really, like, it's not worth the 72 hours to see how good the results are, because what if they're not good? And we're like, well, let's just start, and then 72 hours later we can know, and we can know how we can improve. So I mean, yeah, there's definitely, like, I think in ML we're all, or at least a lot of ML people are very excited about everything, and like, I smile a lot and talk about how hopeful I am about the future. I think chip design is a much more measured, more conservative community, and so it takes a lot to be able to launch in that, given that, I think. And they were definitely very skeptical of these weird looking placements.
So actually, learning from this, Anna, what do you think about human intuition here, right? Are we learning something about that? Because human designs look like they have some properties like symmetry and other regularities, let's put it this way, that your system is not constrained by those things, and so it's generating things in a more free-form way, I would say, right? But do you think that there is some merit to those human, let's say, principles of system design that you could maybe try to inject and see if they actually make it maybe training faster, or maybe help with some aspect also of how much other human designers may appreciate those designs coming up from the system or not?
Oh yeah, that's a very good question. So in terms of human insight, like now once the humans had seen these designs, even if they did look a bit bizarre, they were able to kind of come up with insights into why it was, now that they'd seen this design, that it would help. So for example, like these macros that are placed in this sort of rounded shape surrounding the standard cells, that actually does reduce the wire length needed to connect these macros to the logic gates that they're connected to in the graph. So there is some reason why it helps, but at the same time, like humans would, like the physical designers we worked with were like, well, yeah, maybe like what if regularity, what if this alignment property, what if it helps? Like we should try that. So we actually did try like adding an auxiliary reward function that would kind of impose a more aligned structure. And I mean, it did work. It did create things that looked more like the human placements, but it also degraded the performance. So at the end of the day, I think it's true that really what we should care about is the metrics themselves. I think, yeah, symmetry was another thing that seemed like a good candidate for a human property. I don't remember if we actually imposed that as a cost function. Maybe it would be good to try that. Also, another thing I was thinking was like, so an interesting property of this is that like we have these fast proxy cost functions. So to some extent, we could give feedback to a human physical designer. Like they could make a change and they could see how it affected the quality, or they could see everything that the RL agent can see. And maybe that would result in them being able to generate better placements. But to some extent, like really, maybe it's better if we could just generate a placement in a few hours instead of, you know, having humans spend so much time. And honestly, I've heard from chip designers that really this isn't their favorite part of the process. It's kind of tedious.
Right. So that makes a lot of sense to try to reduce that tedious. Makes a lot of sense.
Yeah.
Yeah, I have another question about this, where this floor planning is situated in the entire process. So is there some interaction as well downstream with things like fabrication, tips, and kind of how this floor planning and design influences the ease of fabrication and so on? I guess I'm maybe not as familiar with this area, although I did ostensibly do an undergrad in electrical engineering, so I should know more, but I'm just wondering if there's these interactions that are maybe not so siloed that influence the design, and if you've considered those.
Yeah, it's a good question too. So yeah, just to be very clear, these results are generated post-place opt. So basically, global placement has been performed, but not like, say, detailed placement, detailed routing. So that's something that happens downstream, but it's a much shorter process, like, you know, a couple of weeks kind of thing, and then it can be taped out. Basically, this is where the physical design team, the TPU team, hands off. So like Google engineers don't move past that point either. So we're basically just injecting ourselves in the actual production workflow.
Another set of questions I think which I was curious about was you talked a little bit about collecting off policy data, and it's interesting that you kind of use that not necessarily to initialize a good representation for your network, but more to pick the right architecture, right?
Yeah.
That 7-hop thing that you were talking about. And I know you also are doing a PhD with Chris Manning, so you are probably very familiar with things around pre-training and BERT and so on. So I'm curious if you've thought about how these ideas for pre-training that kind of have permeated like language could translate to general like system design tasks. And because I think one thing you talked about, like, it would be nice if it could learn a representation that would translate across many different chip design tasks, right? And you're popping out these macros and so on. So I'm just curious, like, what that could look like, and if that's what inspired that direction.
Yeah, that's a really good question too. So actually, it feels kind of silly that we weren't even using the pre-trained weights here. I feel like that's something we can definitely explore, and maybe we would need less fine-tuning to do a good job. So that seems like an obvious direction. And actually, I was pitching like a 20%er like last week, I think, on like we can build better like pre-trained representations of these graphs. So for example, I said that really we're focusing on the representations of edges and not of nodes. But really the nodes themselves also have features, like they even have names, and the names are hierarchical and they tell you something about the function that that node plays, and like there kind of are like hierarchical structures in this chip netlist that the name does capture. So I was kind of pitching them on like, let's build like almost like word embeddings for the nodes that maybe they can help us to design a better pre-trained embedding for the graph. So I think that's an exciting direction too. And maybe I'm biased because I'm interested in NLP and like pre-training language models and such, but I think that would actually help performance.
Yeah, awesome. Yeah, I think, yeah, it would be pretty interesting to see like a chip direct type of paper. However you're embedding these floor plans. Yeah, I think, were there any other questions in the audience? Probably not. I think there was one more question that we missed, which was maybe a detailed question, but like just to throw it in at the end. Does the graph network that you use, the graph neural net, does it have a sense of direction? I think somebody was asking about routing directions and which way things are flowing. So I'm just curious if that's something that you considered in the edge embeddings.
I mean, we don't take that into consideration, but I think actually it is true that nodes drive other nodes, and so there is directionality, and maybe that would be another way that we could improve the representations or capture relevant properties that helped us do better. So that's a good idea.
Yeah, maybe that can be part of the next push.
Tip to macro, yeah.
Awesome. Yeah, I think we're almost at time. So thank you so much for joining us and answering so many questions. It's definitely really exciting work, and yeah, we're definitely very excited to see the next version of the TPU, I guess. When is that releasing?
I can't answer that. But.
Okay, but yeah, well, whenever it is, yeah, we'll keep an eye out for that. And yeah, I want to thank you, Anna, for coming in giving this talk. I want to thank our audience for joining in. And if you haven't already subscribed to our mailing list, just go to mlsys.stanford.edu, subscribe to our mailing list, subscribe to the channel. And next week, who do we have next week, Dan? Do you remember? Sorry, I'm blanking.
Next week, I am checking the website, which you just plugged. Next week, we have Sarah Hooker, also talking about hardware.
Awesome. Yeah. Thanks so much for joining, everyone, and see you next time.
All right. Thanks so much. This was fun.